and Safety Seminar, or PASS. Today, we are fortunate to be joined by Professor Percy Liang, who is an assistant professor of computer science and, by courtesy, statistics at Stanford. Percy also serves as the director for the Center for Research on Foundation Models. And we're very excited to have him on today to talk about open source and science in the era of foundation models.
Okay, great. Thanks for the introduction, Sadaka, and I'm very happy to be here, at least virtually. So my talk is going to be all about open source. And I know what you're thinking. And you're thinking, this is the alignment and safety seminar. So what is this guy talking about open source for? Isn't open source the antithesis of safety? Hopefully by the end of the talk, I'll disabuse you of that notion. And so let me start by portraying how I view safety. So I think a lot of safety can be called product safety today, and it's very focused on the model. And safety, I think, implicitly is today about refusals of misuse. So how do you make a model safe? Is you align it so that if a bad actor tries to get the model to do something bad, the model will say, sorry, I can't help you with that. But I think this is a very limited way to think about safety. And I want us, and I encourage us to think about the broader ecosystem where it's not model-centric, it's ecosystem-centric. There are multiple foundation model developers, multiple users. So then you start thinking about questions like, what are the incentives of these users? What if I'm a bad actor, I'm not going to go to ChatGPT and say, like, I want to spread disinformation. I'm going to factor my problem into pieces and sort of get around some of these safeguards. And I think that is something that's not really quite studied. And then there's an issue of, if you focus on the model, you just think about the model, but it's important to think about the incentives of the foundation model developer and the centralization of power that's happening with the model development, and what are their incentives and their incentives to promote safety or not promote safety. And so, by the way, how are we doing on even product safety, which is just refusals? So this is an example of a paper from a few months ago, where we know that if you have a language model, you ask it to do something bad, it'll refuse. But this paper shows that if you just ask in the past tense, then it happily complies. So this is quite troubling, right? So we're in 2024. People are talking about AGI, and this paper exists. So in other words, we're not doing that hot on product safety, let alone the broader questions of safety. So I want to argue that openness actually is a long-term solution to promoting safety for several reasons. So we know from security, computer security, that this idea of security by obscurity just did not work. You might think that, hey, if I don't reveal my secret sauce on how we do various protocols, then an adversary won't be able to find it out and will be secure. But that just is false, right? And in computer security, what they've learned is that the best way to be secure is be completely transparent about the cryptographic protocols, put the open source code out there for everyone to see, and you have the protocol be open, and then of course your private key is secret. I would also argue that the major obstacle to safety today is scientific understanding. From the jailbreak examples that we've shown, it's clear that we do not have control of our models. We just don't understand how they work, either in the public domain, or I think I would argue in any sort of private organization. And I think it is important that we want academia to be part of this conversation because of incentives, right? It is incentive compatible, not just incentive compatible, is our goal in academia to try to understand these systems. And the companies who are developing models might share this goal, but they also have other goals to monetize the products. And then finally, there are many positive applications, right? And I think a lot of the safety conversation is very sort of reactive, and it's very much about the risks. And of course, there are risks, but I think we shouldn't lose sight of the fact that these are incredible tools. And by making models more open and accessible, it allows us to develop these tools. And later I'll show examples where in cybersecurity where you can potentially patch bugs using language models, which is clearly something that will improve safety and security. Okay, so with this context, let's talk about where openness is today. So everyone, one final thing. So okay, fine. You might think, okay, what if foundation models cause existential risk? Okay, so then clearly you shouldn't be putting out in open source or open weight. And I would argue in that case, I would agree. But I would argue strongly then we shouldn't build it, right? So I think the gap between closed and open is actually far less than people think. And I think if we are really at the stage where these models pose some sort of existential risk, then I think we should stop building. So that's this simple answer. Okay, so now let's contextualize where openness is and what does we mean by openness. So everyone's seen this picture. Over time, capabilities have skyrocketed. And on the other hand, access to models has gone down. So we used to have paper code, data, and weights, and now we just have an API. So why does access matter? Access matters because it shapes research. This is something we don't normally think about because we usually spend our times doing research with the things that we have. But if you look at historically, there are many critical points where access to certain resources has dramatically changed the nature of that research. So in the 1990s, the internet allowed for statistical NLP methods to develop. Without data, you can't do statistics or machine learning, right? It's simple as that. In the 2010s, crowdsourcing platforms gave rise to large entity data sets such as ImageNet and Squad and others. And in the 2010s, of course, we have GPUs, which led to the development and proliferation of deep learning methods. So for foundation models, there are three levels of access I want to talk about. The first is API access to a black box. The second is access to open weights. And the third is full open source access. So API access, the analogy I like to use is you're a cognitive scientist who is staring at this black box, and you can only measure the behavior of it by feeding in prompts and getting responses. Now, this is limited, but I'm going to show you that there are still a lot of questions that you can answer and opportunities for research, namely around building agents to solve complex problems with black box API access. With open weight access, the analogy is that you're a neuroscientist now who can look inside this black box and probe internal activations. Now, true neuroscientists have it much harder than we do. But nonetheless, the opportunity here is to understand the underlying mechanisms behind the computations and the behavior that we were seeing before, and to create novel derivatives, taking this model and chopping off layers and transforming it into a new object. And finally, the open source access. And I think it's important to realize that the previous two axes, why they unlock a lot, you're still living within the confines of the fixed architecture and model weights that are given to you. And open source access, you're thinking like a computer scientist who's building a system that you can control every part of it. And this is something that I think we sort of have forgotten, this level of control. And the opportunity here is to question everything. Why this particular architecture? Why this data? Why this training regime? And I think this is the only way that we're going to do meaningfully deep science on the foundation models and to understand them at a much deeper level than we are capable of doing otherwise. Okay, so throughout the rest of the talk, I'm going to descend this layer cake, starting with the API to open weights to open source. So let's start with the API access. So remember, API access just gives you a black box. You put in a prompt, you get a response. If you're lucky, you get log prompts. The way to think about this API is as this universal function, in quotes. You can use this function by prompting appropriately to do a number of things like summarize, verify, generate. And furthermore, you can compose these API calls into systems, which we can call agents. And important is that the API is actually the controller of execution. It's not called by a fixed program where you just run this fixed set of black box calls. The output of the black box will actually determine what to call next. So here is a basic agent architecture. So there are observations from the world that get fed into this memory stream, which captures everything that the agent has seen so far. Because it's a lot, we need to at any one time retrieve a subset of that that's relevant. And using that subset, we can do one of three things. We can act in the present. This corresponds to generally tool use. We can reflect on the past and summarize or verify what we've done. And we can also plan for the future. And each of these oval rectangles is powered by a black box language model. So I'm going to talk about two types of agents that we can build using this architecture. Problem-solving agents, which are typically the agents that you probably think of when you hear the word agent, and simulation agents, which I think opens up a new host of possibilities. So here's the first work that I'm going to talk about on problem-solving agents. This is an ICML paper led by my student, Qian. And the problem here is something that we're all familiar with. You're given a machine learning problem with some starter code, some data, and your goal is to improve the performance of that machine learning model. So you might go and edit the code, run the code, you look at the training log, and you edit the code again, you run it, and so on. And now the question is, how can you build an agent that does that for you automatically? So here's an overview of what the agent will do. So we prompt the agent, because that's all we can do with these black box LM APIs, to do a few things. One is to reflect on what is going on right now, make a plan, do some fact checking to guard against LM hallucination, think a little bit more, and finally, take a concrete action. Okay, so all of that goes into a language model. It produces a response. And then the response at the end has a particular action with arguments. And that action is actually executed in the environment. This is where code actually gets executed and produces some observation, which could be a training log. And that goes back into the context or the memory stream. And the part of the prompt, for the prompt, we take the last three items or steps in the memory stream and put it into a prompt to give the language model context of what it's actually doing. So the retrieval here is very simple. It's just taking the last three steps. Okay, so how are the results? We ran this over a host of different tasks, ranging from simple categorical competitions to more cutting-edge research and a wide variety of different models. It turned out that at present, Claude v3 works the best, but you notice also that the accuracies are widely varying between solving or doing very well on the classic benchmarks, but nearly not doing anything on the more advanced research benchmarks. So there is a bunch of work happening in the sphere of building research agents. One thing I think is exciting about this line of work is that this is not any arbitrary task, any arbitrary agent benchmark. It's a special benchmark where if you solve the task, you can actually improve machine learning itself, improve the model, which will then enable you to solve the task better. So this leads to a potential virtuous cycle of self-improvement, which I think is really exciting. So the second task I want to talk about is on cybersecurity. So this is a project with a lot of students led by Andy. So here the task is as follows. You're an agent. You're given access to a server, and you have access to the source code of the server. And you have the ability to execute arbitrary commands on the bash shell. Okay, so the agent is going to, the goal is to basically hack into the server. It's read the code, identify the security vulnerabilities, exploit those vulnerabilities, and then retrieve a hidden key called the flag. So these are called capture the flag tasks. And so this has, the nice thing is that this has a very simple quantitative evaluation. And to make this task easier, because these are really advanced tasks, we break the task into a bunch of subtasks, which we can optionally use to guide the agent. So the agent architecture is the same as before, roughly. You have an initial prompt. We ask the agent to reflect, plan, think, and then execute an actual command that produces a observation, which goes into the memory stream, and you iterate. So the results, we collected a set of CTF, capture the flag benchmarks, and we ran a bunch of different models on them. And the best model was, again, 3.5, Claude 3.5, and it was able to solve 17.5% without any guidance, any subtasks. Interestingly, the benchmarks, the tasks have a wide variety of difficulties as measured by the first time humans competitors were able to solve the task. So the hardest benchmark took a team of human competitors 24 hours, and the hardest task that language models were able to solve took humans 11 minutes. Okay, so there's quite a big gap here between what teams are able to do and the language model. And since then, these results have actually improved with better agent architectures and stronger models. So, there is a connection to safety here. Again, this is not an arbitrary agent benchmark. It's a very special and important one for two reasons. One is that if you think about this safety, cyber risk is often cited as one of the primary threat vectors, where if agent stacked by language models get good enough, we might imagine a very different world in which cybersecurity is compromised. And so this benchmark serves as a risk assessment tool to inform AI policy. The other side of things is that many cybersecurity experts build penetration testing tools. So these are tools that you run against a system pre-deployment, potentially, to uncover vulnerabilities so you can fix them so that we have a safer system. So the development of SciBench, as well as language models in general, is dual use in this way. And what the sort of offense and defense balance looks like is actually very open in my mind. And I think it's important to have this very balanced view of these tools and not just focus excessively on the risk. Just because these tools can be used to hack doesn't mean that it is a net negative, because of the potential for defense. And I alluded to earlier that these tools can also be used to patch vulnerabilities, which is clearly in favor of defense. Okay, so now let me turn to simulation agents. We've talked about two types of problem-solving agents in machine learning engineering and cybersecurity. So this is a paper led by my student Jun Park from last year called Generative Agents. And the goal here is to build a simulation of a society, small society of people, where the people go around their daily lives and interact with each other. And the goal is to see how well they can mimic humans. And the architecture is the same as before. Actually, this image comes from that paper. I'm going to focus on the retrieval and reflection part of things, because that's what's perhaps a little bit different than before. So the memory stream, remember, is record of everything that happens before. And if you just reflect on your daily lives, there's a lot of things that happen that are not that interesting. Like the bed is being used, the refrigerator is idle. But nonetheless, all of these things get recorded because you never know what you might need. So that means retrieval needs to do something non-trivial. Before, we were just taking the last three items in the memory stream, which isn't going to work here. So here we have a function that takes into account recency. More recent things are more likely to be retrieved, how important something is, and how relevant something is to the current context. So retrieval happens based on these three indicators. The reflection part is also interesting. So memory stream, remember, is a lot of information, very low level. And for the agent to make more meaningful high-level decisions, reflection is a process we use to turn these low-level observations into higher-level concepts. So for example, a low-level action might be Klaus is reading about urban design. And upon reflection, we ask the language model to reflect on that and generalize. And this might lead to, via a chain of, or a tree rather, of reflections, something higher level like Klaus is highly dedicated to research. And this can inform future actions and plans and so on. Finally, the one special thing about humans is that they're social animals and they talk to one another. So it is important for us to simulate that aspect of things as well. So these agents talk to each other. And one thing that's interesting is that we can simulate information diffusion. So Isabella is throwing a Valentine's Day party. She invites a bunch of people and they talk to other people and the information might come back. So you get this sort of rich information diffusion that happens through these LMs talking. So now, one thing that we haven't done so far is that these are fictitious agents. And we were able to show that they generate believable behavior, but what about realistic behavior? So let's make it real. And this is a follow-up paper that just came out a few weeks ago called Generative Agents Simulations of 1,000 People, led by June as well. And the key here is that how do we make these agents more believable? How do we pack the richness of a human experience into a person? And interviews are answer. So this is an example of a pilot interview that we did with June. The interviewer starts, tell me the story of your life. And June says a lot of things. And you read this, you realize the richness of the interview. You not only get factual information, but you also get a perspective of how June was, feeling about moving from, Korea to Boston. So to operationalize this, and to scale it, we recruited 1,000 people from across the U.S. From different demographic groups. Each person undertook a 2-hour audio interview, which was administered by an LM agent. This produced for every person an interview transcript, like the one shown on the previous slide. And that serves as the agent's memory. So now you have real person, simulated person. And we want to know how close these are. To do that, we had the people run through a battery of different surveys, personality tests, economic games, behavioral experiments, and we had the agents do the same. And then we measured basically how accurate the agents were predicting the humans. So the answer is that it was pretty good. So first of all, humans are not self-consistent with themselves. So they're about 81% consistent with themselves. And so the accuracy of interview-based agents with respect to the humans was 69. So you can think about this as 85% normalized accuracy. So we're capturing 85% of the signal of the humans just from this 2-hour transcript. So just to reflect in general on agents and API access. So we use these APIs to create agents. We can solve complex problems in ML engineering and cybersecurity. We can also simulate people. And this is very exciting because we can essentially build a digital twin of society. We're not there yet, but I think that's sort of the long-term agenda of this line of work, which is exciting for social scientists because for the first time, you can actually do kind of large-scale controlled experiments using these simulacra. But so far, we've only looked at static agents. And what we really want these agents to do is learn from experiences. And for that, you need deeper access. So one analogy I like to use is that we sort of reached this sort of, in terms of AlphaGo, the supervised learning part of the trajectory where we've trained these large language models and mostly on imitating human behavior. And now these agents give us an environment for these language models to go and take actions. And if we can find a reward signal for this, then it opens up another level of improvement based on reinforcement learning. Okay, so that was API access and all the things you can do with that. Now let me turn to open weight access. So remember open weight access, you have access to the weights. More accurately, this should be called dual use foundation models widely available weights. This cumbersome language comes from the executive order from 2023. And the reason it's widely available and not completely available is that these models, such as Llama, have license restrictions, for example, for companies that have over 700 million monthly active users. So just a little footnote here. One advantage of open weight models is reproducibility. So if you have a closed API model, models get deprecated. And once they're deprecated, you can't reproduce the result anymore, and it's sort of lost in history in some sense. Whereas if you have open weight models, you could always have them. You can put them on your laptop, under your mattress, download them from Hugging Face. And that allows you for much more controlled and rigorous experiments. I'm going to go through a bunch of work that is leveraging open weight models. So this is a work out of a new nonprofit called Transluce. And here, what they tried to do is to understand why a model is having a certain type of behavior. So if you take Llama 3.1 API instruct, and you ask it which is bigger, 9.8 or 9.11, it says 9.11 is bigger than 9.8, which is wrong. And if you just had API access, you would be scratching your head. Why is it doing this? But because we have open weight access to Llama 3.1, Transluce built a tool that allows you to annotate each neuron that's firing with a natural language explanation. And then that allows you to look at what is happening when the model is predicting 9.11. And it turns out that that neuron that's being activated is associated with these 9/11 attacks, which means that 9/11 is actually triggering in potentially being interpreted as a date. And if these are dates, then 9/11 is definitely after 9/8. So this is not a fully rigorous explanation, but it does provide this qualitative insight into what is actually happening inside this black box. And like I said before, one of the bottlenecks, or probably the bottleneck for safety long-term, is just understanding what these models are doing. And with open weight access, you can better understand the system that we're dealing with. Here's another example from NVIDIA. So this paper takes a large model, a 15 billion parameter model, and prunes away some of the layers and does some distillation, shows that you can produce much smaller versions of this at a much cheaper than training from scratch. So this is an example where access to models allows you to do the surgery that produces new artifacts. This is another example which has some safety ramifications. So this paper took an open model, llama, and by using the gradients of that model, they were able to essentially craft an adversarial prompt that jailbreaks that open model by basically doing optimization over the prompt. And this requires gradient access and isn't possible on closed models. But the really interesting thing is that you take this prompt and you feed it into OpenAI, and it will actually work and jailbreak OpenAI as well. So this is an interesting thing where open weight models, not even open source, open weight models has ramifications for safety on closed models because of some, not very well understood transfer that happens here. Okay, so I'm going to spend a few more moments talking about one particular work from my students Sally, Ahmed, and Rohit that I think is not only just leveraging the existence of open weight models, but is inspired by the presence of open weight models. And here's the motivation. If you go to Hugging Face, there's a lot of models out there. And some of these models are trained from scratch. Some of them are fine-tuned from others. And the broad goal is just to understand what's going on in this ecosystem. Because for the safety of open weight models, while we can't control what people do when they download them, we can at least hope to understand the provenance of where models are coming from. If there's some models that are violating licenses and so on, we can kind of track things better. So here's the crisp version of this problem. Okay, so given two model weights, theta 1 and theta 2, are these independently trained or not? And if they're not, it could be theta 1 was fine-tuned from theta 2 fine-tuned from theta 1, they were fine-tuned from a third model, and so on. Okay, but I'm just testing for independence here. So how do you do this? Well, one thing you could do is you just compare some cosine similarity of the weights. The problem with this is that you get a number, a similarity metric like 0.1. What do you make of that? Is that similar or not? Well, I don't know. Where do you set the threshold? And how can you get any statistical guarantees? So that's not going to quite work. But one thing you can do here, and this is more of a thought experiment. So suppose you knew how theta 1 was created, and in particular, it was created by this train function with some random initialization. So what I'm going to do is I'm going to train a bunch of theta 1 clones, which are all independent of each other. And now the key insight is that, well, if theta 1 and theta 2 were actually independent, this statistic should look no different than one of a similarity between theta 1 prime and theta 2, from where theta 1 prime is an independent clone. Okay, but if theta 1 and theta 2 were dependent, then this statistic should look odd. And from this, we can construct a p-value, which we basically measure the fraction of times that an independent version is more extreme than the statistic that we observed. And that's a valid p-value for the hypothesis that theta 1 and theta 2 are independent. Okay, but the problem is that it's impossible to train to get theta 1 because we only have theta 1. We don't know how it was trained. And even if we knew how it was trained, we probably wouldn't want to expand the compute to actually train a bunch of models just to do this test. So we need a new idea. And the new idea is basically we want to get a bunch of models that look like theta 1 without actually retraining. And here we're leveraging some invariance properties of the models where you can permute the hidden units defined by the model theta to get a bunch of counterfactuals. So what you do is you take a matrix and you just permute the weights. And you have to do it for multiple matrices and coordinate them. But the basic idea is you permute the weights. And so then for each of these permutations, you can think about that as a theta 1 prime from before, and using the same rationale, you can construct a valid p-value. Okay, so this is a very simple test. It's very cheap to run. It involves no training. So how well does this work? So we validated this empirically by looking at the subset of the Hugging Face ecosystem where we understood what models were independent and dependent. These are all Llama 2 architecture models. And we found that for the models that were fine-tuned from Llama 2, we were able to find that the p-values were very small, which means that they were not independent. And for the models which were independent, the p-values should be uniformly distributed and all over the place, which they are. So this test works extremely well. So you normally think about, how small a p-value you need. This p-value is basically underflown, so close to basically 0. So we also looked at a bunch of fun use cases. So at some point, there was a controversy around this mysterious model MICU 70B, which was leaked, which was later confirmed to be a fine-tuning of Llama 2, confirmed by the Mistral CEO. And indeed, we were able to verify that these two models were indeed not independent. We were able to find that the striped hyena model, which took Mistral and injected other hyena, which is a different architecture, layers in between, were also not independent. So these two have different architectures, but we were able to still identify that. And finally, Llama 3, the 3 billion model was released, and it was described to have been derived from the 8B model. And again, we were able to not only verify that, but our test actually gives you more precision and tells you which layers were actually derived from which other layers, which was not something that was disclosed in the actual blog post. Okay, so just reflecting open weight access, it's clear that strong open weight access has been immensely valuable for a bunch of research, and in particular, safety research. It enables research on interpretability, fine-tuning, distillation, merging, and it's all reproducible because you have the weights forever. I think one general question of what you can do with open weight is that we're making weight modifications or looking inside, and how these map onto coherent functional changes is an open problem. And oftentimes you have to fine-tune the models to kind of smooth out some of the damage that you get when you just rip out different parts of the model. This teaches about API models because of some mysterious transfer between open and closed models. And finally, it also introduces new types of problems that are motivated by open weights. Again, the open weight ecosystem is here to stay. It's going to exist. And we need to think about safety and also just general understanding of what is happening in open weight, developing stronger monitoring tools and so on. And this opens up a whole new line of research. But all this said, we're still operating within the confines of the blueprint of existing models, the Llama 2 or Llama 3 architecture. And to go beyond that, we need to look at open source models. So the good news is that there are a bunch of different open source language model developing efforts originally from Eleuther, AI2, Hugging Face, and so on. The bad news is that open source models are still well behind closed source models. And I think these numbers have gone up a little bit, but there's still quite a big gap. But backing up a little bit, what is open source? So the term open source comes from, of course, open source software, which has a rich history, starting from the 50s with a hacker culture in MIT, or if you think more broadly, academia for centuries has been all about openness and science. And both of these roots share the idea of creativity, exploration, transparency, collaboration, and resistance against authority. And open source software has been dominated by the kind of two leading figures, Richard Stallman and Linus Torvalds, who created the foundation of open source software, which has then kind of been really prominent and dominant in computer science. But it wasn't until '98 where the open source initiative was created and the term open source was coined. And now the open source initiative is trying to define what it means for open source AI system. And they define it in terms of four freedoms: the ability to use a system without asking for permission, the ability to study it, to modify it, and to share it. And more in the weeds, the AI definition demands for an AI system to be open source that all the weights need to be made available under the OSI approved terms. So this is stronger than open weight, which is just widely available. So Llama wouldn't count even under this. Moreover, the code used to train and run the system should be open. And this is not just the training code, but it's also importantly includes the data processing code. And we know that data is sort of the secret sauce that goes and defines and shapes the model behavior. That needs to be open as well. And finally, data information, the description of the data. And you might wonder why data information, but not the data set itself. And this is because of legal reasons. The model developers do not own a license to the web data, which is generally copyrighted. So they don't have the legal rights to actually release it and to distribute it, even though this sort of typically happens sometimes. So you don't want a definition of open source that is, in order to satisfy, you have to do things which are not legal. So one other thing about open source that I want to stress, which is not under the scope of OSI, is if you look at modify. So for code, this is easy because you can take the source code, you can change it, you can recompile it if necessary. But for models, this is actually a big lift. And this is because in order to change a model, you might have to retrain it, maybe from scratch, but even if not from scratch, you would have to probably fine-tune it for quite a few epochs. So you need compute to retrain to really achieve the open source spirit beyond just the OSI definition. So now I want to highlight a few works from my group that have leveraged open source, or at least the ability to retrain. So this project was Do-Re-Mi, and the question is, what data mixture should you use? So typically language models are trained from a combination of different sources, but these weights are generally set by hand. And we developed a method based on distributionally robust optimization, which sets them automatically, and this leads to a 2.6x speed up over manually tuned weights. Another project that we worked on was on defining a new type of optimizer that leverages second-order information, basically diagonal Hessian with clipping. And this provides a 2x speed up over Atom. And of course, this requires retraining because you're changing the optimizer. And then finally, on the model architecture side, we develop a new type of architecture alternative to a vanilla transformer, which has some interpretability properties. And in particular, allows for precise model edits where you can change, for example, MacBooks to be created by HP instead of Apple. And this is like a very surgical edit without relying on fine tuning. It works much better than just blunt fine tuning. So all these works are made possible by the ability to train. But the question I often get is, well, do these results hold if we scaled up? In other words, how can you get the compute to actually prove out these results at scale? And for this, it's a hard question, and I'll give you three answers to that. One is that let's try to double down on scaling laws. So typically you think about scaling laws as extending out to larger and larger scales and predicting larger runs. But in the other direction, I think we need to develop scaling laws that extend down to scaling laws that allow people to work at smaller scales, but with an eye on how these methods will work at scale. Track two is there are actually quite a bit of compute outside the big data centers. They're just sitting around idle. And I know everyone's probably thinking, well, I always have the cluster is always full. And that's mostly true, but there's pockets of idleness. Just last week during Thanksgiving, the cluster was, I'm sure, much emptier than it was normally. And if you can only harness these GPUs, then you can maybe actually train a large model. But the problem is that the interconnect between GPUs, which are geo-distributed, is actually much worse than within the data center, often by like 100x. One of the papers that we published 2 years ago had some promising results that showed you could train models at this is on 1B scale, only 2x slower than if you did it in the data center, whereas the interconnect was 100x slower. So 2x is not a bad penalty to pay if your interconnects are 100 times slower. And since then, there's been other works. The DeepMind folks have introduced new algorithms that allow for better decentralized training. And there's some efforts from Prime Intellect. We're training a large decentralized training run of a 10 billion parameter model, which I think has finished. And I think this is really exciting because it allows us to be creative in how we use our compute and amass it. Track three is just convince people to fund a large-scale scientific research. So the NAIR, the National AI Research Pilot, was created in order to provide larger amounts of compute for public sector AI research, and hopefully efforts like this can be scaled up to allow for more and more open source work. And if you look at other disciplines, they sort of figure it out. So from biology to astronomy to physics, where these kind of big science projects have been undertaken, where there's a recognition among the scientists that there needs to be a large investment, multi-billion-dollar investment in the infrastructure to build an artifact that can lead to new types of science. And I think this is something that we need to do in AI as well. So to conclude, we've looked at 3 different types of access to foundation models. And I think it's important to remember that access shapes research. So while you're doing research, think about the types of access you have and think about the confines that your kind of assumptions that you're living with. And I do think that there is a lot of interesting work to be done with just API and with open weight models, which I've alluded to. But I think it's important to realize that most of this research, increasingly large amounts of it, live within the confines of APIs and fixed weights. But I think in order to get a true understanding of these models, this API with fixed weight is definitely not enough. We need to be able to question everything, the data, the model architecture, the training algorithm, and need to be able to train from scratch so that we can get out of this local optimum and improve our understanding of these models. And I think if you think about what is machine learning, understanding machine learning about, it's about this mapping from data and the model architecture and the training algorithm and those inductive biases leading to model behavior. And this was really hard, even with full access. And it's so hard with full access. And of course, it's impossible with if you only have API and fixed weights. And finally, to connect back to safety, I do believe that understanding is the critical bottleneck for long-term safety. In the short term, I think we can do a lot of things to better align our models and do better product safety. But I think long-term for safety, we need deeper understanding of our systems. And then big bottleneck is compute. And I think there's many things we can do. We can try things at smaller scale, but think about scaling laws and what happens at scale. We can try to pool our compute. And hopefully by doing this and being creative about how we can leverage our resources, we can achieve more together than we can do individually. Okay, with that, I'll conclude my talk and I would love to take questions.
Thank you, Percy. It's a very interesting talk, very far-ranging. Yeah, so we'll just jump right into the questions. So the first question, which is maybe coming from someone who has, meaning me, someone who has not thought too much about the challenges perhaps about open sourcing, is that if you were at a company and you invested millions of dollars into making a model, how would you justify kind of like to your board or to like wherever you're getting this money from that you're now going to open source and essentially give away this very expensive thing for free?
Yeah, I think it's all about incentives, I think, as you put it. I think on open weight releases, clearly this has worked at Meta, right? It is at some level, it is spending, hundreds of millions of dollars training models and just quote unquote giving it away for free. Of course, the and of course, I think we are not just I'm not just interested in open weight. I want to go to open source, which is I think even harder. But if you look at the history of open source in software, none of it is philanthropic, right? The reason that Linux exists is because IBM invested $1 billion in Linux at the end in 99, 2000, because they wanted to fend off the Microsoft monopoly at the time, right? And so our companies can make strategic moves and a large investment in open source because open source fundamentally commoditizes the thing that you're open sourcing, right? And by commoditizing your complement, that can be, from a commercial perspective, advantageous. So I think the trick to making open source foundation models succeed is to figure out these incentives and get companies and government and philanthropy kind of aligned on the goals. I think it is obviously a very extremely challenging thing because it sounds good, but it hasn't happened yet. But I do think that is possible to make progress on this front.
Yeah, thank you. And kind of to follow up on that, I was also wondering, what do you think are the desired and realistic level of open sourcing these models? So earlier in your talk, you mentioned that maybe open sourcing these data is pretty challenging due to copyright and legal concerns. So what about the methods that people use to train these models on, and what about the ablations they run? In your mind, what are some of these kind of actionable next steps as we move towards open sourcing more than just the weights themselves?
Yeah, I think it's a good question. And it's obviously a spectrum, right? I've sort of looked at it in terms of 3 layers, but I think a lot of things could help. More technical details about open weight models, I think could be help. I think that, for example, there's very little information about the data right now and how it's processed and so on, which could be very valuable in understanding how behavior arises. There's intermediate checkpoints, I think could be very valuable to understand training dynamics. I think that there's that's just kind of on the open way side. I think on the open source side, data release is challenging right now in the current legal climate with all these big lawsuits kind of flying around. Maybe next year we'll get a bit more clarity on that. I think methods and code, this in principle should be possible, right? Because the sort of the moat here is like the compute. If let's say a foundation model developer released its code, it's not that easy for another organization to just like use it and train a model if they don't have the resources. But it would help us understand better how this model was created. But I think one challenge is that there's sort of the challenge that people at companies are busy doing things and trying to, make their models better. So the incentives of just open sourcing for science is not enough, which goes back to the point that for open source to work, I think there has to be, the incentives have to be that open source is actually going to help the company in some way.
Yeah, that's interesting. I do see how all these concerns kind of come together, they weave together. So I think that we're actually out of time, so we didn't get around to all of our questions, but thank you so much for speaking in the seminar. And yeah, thanks everyone for tuning in. Hopefully you check out our other talks and our future talks as well.
All right.